This is the first lesson in a unit about the properties of gases. In previous lessons, we focused on the properties of solids and liquids and gases and how they're different from each other. But in this chapter, we're focusing specifically on gases and their properties. So, for example, if we look at these two pictures, hopefully it's obvious which one is a gas. We can see that the one on the right is a gas, and one thing that gases pretty much all have in common is that the molecules are very far apart from each other compared to the molecules of this state of matter over here, which seems to be a liquid, because the molecules are not in any type of orderly crystalline structure, so we know it's not a solid. So the one on the left is a liquid. On the right, though, that's a gas. Now, if we look at that, we can decide some fast facts about a gas. We can say that gas molecules, as you saw in that picture, are very far apart from each other. And because they're so far apart, it's pretty easy to squeeze those molecules closer together. And that's called compressing a gas. And so if you've ever taken a medicine dropper or some type of a syringe like that and kept your thumb over the end of it, you can push down the piston and push those molecules of gas closer to each other. It's very easy to compress a gas. And since a gas can be compressed, then I suppose we can also cause a gas to expand, to fill a container. And as it turns out, a gas is the only one of the three main states of matter that can do that. It can actually expand to fill a container. And so if you have a gas and release that into a room, it's eventually going to diffuse out and fill the whole room. Now, all gases have four properties. And these are four properties that we can change, we can manipulate about that gas. Now, the first thing that we can look at or measure in a gas is its pressure. And the pressure is sometimes measured in atmospheres, although it can be measured in pascals or kilopascals or millimeters of mercury or psi. And pressure is basically just determined by how often the gas molecules are colliding with the container walls. And so if you have an enclosed gas, perhaps in a balloon or some other container, and you have a lot of gas molecules, you're going to have a lot of collisions, and so the pressure is going to be higher. Well, if you take those gas molecules out, you aren't going to have as many collisions with the walls of the container, so the pressure goes down. That's pretty much all that pressure is determined by, how often the molecules are colliding with the walls of the container. We also can measure the volume of a gas. The volume is just how much space or how much room that gas takes up. We usually measure volume in liters, although we can use other units as well. Also, temperature is a property of gases. In a previous lesson, we learned that temperature is just a measure of the average kinetic energy, so pretty much the mass, but for our purposes, basically how fast the molecules are moving, their velocity. And that's usually measured in degrees Celsius or in kelvins. Sometimes we could measure it in degrees Fahrenheit if we really wanted to. And the other property that sometimes we forget about is the actual number of gas molecules we have. And so in a container, perhaps a closed container of gas, we can say that it has a lot of molecules or very few molecules. And since molecules are really, really small and they're hard to count, we measure them in moles. And so we've had a discussion about that in the past, about how to count the number of moles. And so these are four properties of a gas that we can change sometimes and we can manipulate. And so those are the four properties that we're going to be looking at in today's lesson. Now, there are four gas laws that we're going to look at in this lesson where we're going to be manipulating some of these properties. And today we're going to be focusing on the first three, so pressure and volume and temperature, and in a later lesson we'll talk about number of gas molecules. The first gas law has to do with pressure and volume, and it's called Boyle's law. And this was one of the very first scientific laws ever produced in science. This is well over 300 years old. And Boyle's law basically states that the pressure of a gas is inversely proportional to its volume. Now, Notice that I have inversely proportional highlighted here. It's in bold. That means that if one of the factors goes up, the other factor goes down. And so, for example, if we have a closed gas and you make its volume go down, it makes the pressure of that gas go up. And you can go in the other direction too. You make the volume go up, it makes the pressure go down. And so, since this is a scientific law, you might recall from earlier in the course we said that laws just state what happened. They don't try to explain why, but they usually do have some kind of a mathematical equation associated with them. So here's the equation that goes along with that. P1 V1 equals P2 V2, where P1 is the initial or the starting pressure, V1 is the starting volume, and P2 would be the final pressure, and V2 is the final volume. So we have the ones represent the starting conditions of the gas, and then the P2 and the V2 represent the ending or the final conditions of the gas. So let's try an example here, and we're going to see how this works. Here we have a balloon that's filled with 30 liters of helium gas at 1 atmosphere. What is the volume when the balloon rises to an altitude where the pressure is only 0.25 atmospheres? So we're going to essentially mine the information out of the problem and plug it into the equation. So here we're going to plug and chug. And so P1 is the starting pressure, and hopefully you see that that's 1 atmosphere. So we're going to plug into the equation 1 atmosphere. And then we have V1, which is the starting volume, and that's 30 liters. And that's equal to P2, which is the final pressure. The final pressure is 0.25 atmospheres. And then we have V2, which is the final volume. That's what we're trying to solve for, because the question asks what is the volume at this new condition. So we're going to be solving for V2. That's our unknown in this problem. So now we just have an algebra problem, and so we can take 30 times 1 and divide that by 0.25, and we use algebra to solve for V2, and it is 120 liters, and so that's the answer. So that's all we have to do to use Boyle's law. Now there's another gas law that involves volume and temperature, and this one is called Charles' law. And this one states that the volume of a gas is directly proportional to its temperature. And so once again we have this term here, directly proportional, and basically what that means is that if one of the factors goes up, the other factor goes up as well. One factor goes down, the other factor goes down. So what that's saying is that if you raise the temperature of a gas, it makes the volume go up. And if you lower the temperature of a gas, make it colder, the volume goes down, it contracts. And so if you've ever seen a water bottle that's closed, sealed up, and you put it in a freezer, this bottle is otherwise empty other than the gas. In the freezer it's going to contract because of Charles' law. The temperature goes down, the volume goes down. There's an equation that goes along with this. V1 over T1 equals V2 over T2, where V1 is the starting volume, T1 is the starting temperature, V2 is the final volume, and T2 is the final temperature. Now there is a catch here. The temperature has to be in kelvins, and so I'm going to make a note of that. Temperature has to be in kelvins. And if for some reason the temperature that's given to you is not in kelvins, then you have to convert it. And you might remember that equation that we learned very early in the year, Celsius plus 273 equals kelvins. And so we're going to need to convert those quite often. So let's try an example with Charles' law. A balloon in an air-conditioned room at 27 degrees Celsius is inflated to a volume of 4.0 liters. It is then heated to a temperature of 57 degrees Celsius. What is the new volume of the balloon if the pressure remains constant? So once again, we're looking at this problem. It looks like the volume is changing and the temperature is changing because we start with 4 liters and then it asks us about some new volume, and the temperature is changing too because it goes from 27 degrees to 57 degrees. So we're going to have to use Charles' law, that equation right there. So we're going to plug and chug once again. So V1 is the starting volume. That's the 4.0 liters. And that's over T1, which is 27 degrees. But remember that we have to convert that to Kelvin. So 27 plus 273 is actually 300 kelvins. And that's equal to V2. Well, that's what we're trying to solve. It says, what is that new volume? So V2 is our unknown in this problem, and it's over T2. And the final temperature is 57 degrees Celsius. If we add 273 and convert that to kelvins, I think it's 330 kelvins. So now we have to solve for V2. And probably the best way to do this is by cross-multiplying. So 300 kelvins times V2 equals, in that direction, we have 4.0 liters times 330 kelvins. And so now we just multiply and do a division there. And my answer, when I plug that into my calculator, is that V2 equals about 4.4 liters. And so hopefully you get an answer that's very close to that when you solve this problem as well, 4.4 liters. So that's how you do a problem with Charles' law. Now there's another gas law that involves pressure and temperature. You see, earlier we had pressure and volume. Charles' law is volume and temperature. Well, the next gas law is pressure and temperature. And this gas law is called Gay-Lussac's law. And this gas law states that the pressure of a gas is directly proportional to its temperature. So this is Gay-Lussac's law. If temperature goes up, the pressure of that sealed gas goes up as well. The temperature goes down, the pressure goes down as well. Maybe you've seen this. If you've seen an aerosol can that's sealed on the side, there's usually something that says, do not throw into flame. And that's because if you take that empty aerosol can, even if it's empty, and throw it into a fire, it's going to increase the pressure of that can when it gets superheated, and it's going to cause the can to blow up. Maybe you've seen the opposite. If you've taken a can of air, as they're sometimes called, to clean your computer keyboard. If you press the button and release the air out of there, it causes the pressure in the can to go down. And it also causes the temperature to go down. So that can feels cold when you release the pressure in it. So this is just a good application of Gay-Lussac's law. Here's the equation that goes along with that. P1 over T1 equals P2 over T2, where P1 is the starting pressure, T1 is the starting temperature, P2 is the final pressure, and T2 is the final temperature. And once again, temperature has to be in kelvins. And so we need to get in the habit of converting those temperatures to kelvins, just like we did with Charles' law. So here's an example with that gas law. A tire has a pressure of 20.0 psi when the temperature is negative 17 degrees Celsius. What will the tire pressure be when the temperature goes up to 30 degrees Celsius? So once again, we have Gay-Lussac's law. So we're going to plug and chug because we can see that the pressure is changing from 20 psi to some new pressure that we have to calculate. And the temperature is changing also from negative 17 degrees to 30. So we're going to plug and chug into that equation. So P1 is the starting pressure, and that's 20.0 psi. T1 is the starting temperature. That's negative 17 degrees Celsius, but we convert that to Kelvin, so it's 256 kelvins. And then that's equal to P2, which is what we're trying to solve for. P2 is our unknown, over T2. The final temperature is 30 degrees Celsius, so we convert that to kelvins and write that as 303 kelvins. And so once again, we now have to cross multiply. So in this direction, I'm going to cross multiply. We get 256 kelvins times P2 equals, and in the other direction, we get 20.0 psi times 303 kelvins. And so now we just have to multiply on the right side and divide by 256. And using algebra, I get that P2 equals about 23.7 psi. And that's a reasonable answer because we raised the temperature, so we expect the pressure to go up. So this is a good example of using Gay-Lussac's law. We have one more gas law, and this is where we take all three of those gas laws, Boyle's law, Charles' law, and Gay-Lussac's law, and put them all together. And when we do that, we get something called the combined gas law. And it's basically the first three gas laws we mentioned just all combined. So it's going to look like this. P1 V1 over T1 equals P2 V2 over T2. Of course, the temperature has to be in kelvins, just like it has been in all those other gas laws. So temperature always in kelvins. So let's try an example with the combined gas law. And you'll notice that this time we have a problem that looks a little bit lengthier. We have more numbers to deal with here, and that's because there are more variables. A container with an initial volume of 1.0 liters is occupied by a gas at a pressure of 1.5 atmospheres at 25 degrees Celsius. By changing the volume, the pressure of the gas increases to 6.0 atmospheres as the temperature is raised to 100 degrees Celsius. What is the new volume? So we know that this is a combined gas law question because the volume is changing. It goes from 1.0 liters to some new volume. The pressure is changing from 1.5 atmospheres to 6.0 atmospheres, and the temperature is changing too, from 25 degrees Celsius to 100 degrees Celsius. So once again, we're going to use the combined gas law. So P1 is 1.5 atmospheres. That's the starting pressure. And then V1, next to it, is the starting volume. That's 1.0 liters. On the denominator, we have T1, and that's 25 degrees Celsius is our starting temperature. We change it to kelvins to make it 298. Then on the other side of the equal sign, we have P2, the final pressure, and that is 6 atmospheres. And that's next to V2. Well, that's what we're solving for. It says, what is the new volume? So that's going to be our unknown. So V2, we don't know what that is yet. And then T2 on the bottom, the final temperature, is 100 degrees Celsius. So when we convert that to kelvins, that's 373 kelvins. So from this point, we just have a math problem, algebra problem. So we have to cross multiply. And we cross multiply in this direction. We get 298 times 6 times V2. And so that is 1,788 times V2 equals, and then when we cross multiply in this direction, 1.5 times 1 times 373 gets us 559.5. And so to solve for V2, we just divide both sides by 1788. Now be very careful here because some students can get this far, but then they mess up on the last step. Remember, when you're solving for a variable, we divide by the number that's next to the unknown. So we divide by 1788. And so 559.5 divided by 1788 is about 0.31 liters. And so that's the answer. So this is a good example of a combined gas law problem. And so at this point, you should be able to solve problems using Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law. Now, sometimes students will wonder, how do you know which equation to use? Well, the key is look at what's changing in the problem. So for example, in the problem we have on the screen here, pressure, volume, and temperature are all changing in the problem. So, PV and T, that's the combined gas law. If you have a problem where it's only pressure and volume that are changing and the temperature is not changing, well, that's P and V. That's Boyle's law. And if you have an equation or a problem where volume and temperature are changing, well, that's V and T. That would be Charles' law. And so using this idea and these examples, you can solve problems using any of those 4 gas laws. And so all you have to do is plug and chug with Krug.